Hello. In this video, we briefly discuss our framework and illustrate the emergent behavior of a robot under admissible and admissible winning strategies. Let's consider a scenario where a robot and another agent are operating in a grid world as seen on the right. The goal of the robot is to reach the goal state in green while always avoiding the environment player in blue. Both agents can take a step in each cardinal direction. To enable strategic decision making for the robot, it needs to 1. Interact with other agents, and proactively reason and react to their actions. These properties can be naturally modeled using a two-player quantitative game where the game abstraction captures the interaction and a payoff function models the quantitative constraints like energy budget. Thus, the problem we consider is, given an energy budget, synthesize a strategy for the environment player to finish task V. Traditionally, this problem is modeled as a reactive synthesis problem, and a winning strategy is synthesized, assuming the other agent is purely adversarial. Unfortunately, a winning strategy does not exist even for trivial scenarios. In our grid world, environment player has an adversarial strategy to always block system from reaching the goal state. In this paper, we address this problem. We explore alternate notions of strategies that allow system to do its best. We use the classical notion of dominance to rank the system strategies. Then we say a system is playing its best when it is playing the highest ranked strategy. Prior works that use dominance to rank system strategies can be categorized as best effort synthesis and admissible strategy synthesis. In best effort synthesis works, they model the interaction as a two-player game with qualitative objectives using LTLF. These works do not consider quantitative objectives like we do, and the strategies are value preserving, which implies that every winning strategy is best effort. Finally, the algorithm is a fixed point based computation, which makes it computationally attractive. Admissible strategy synthesis consider two-player games with quantitative as well as qualitative objectives. However, the objectives are defined over infinite races, unlike robotic tasks that need to be finished in finite time. Moreover, these strategies are optimistic, that is, they are not value preserving. This implies that a winning strategy is not always necessarily admissible. Finally, they give a sketch of their algorithm using parity games machinery. In this work, we consider admissible strategies for two-player reachability games with quantitative objectives where the task must be finished in finite time. We are the first to consider this problem. We formalize the notion of dominance for a total payoff function over finite traces that was not studied before. We provide necessary and sufficient conditions for their existence and give a simple yet efficient synthesis algorithm that involves a graph search and two fixed point computation. We prove that admissible strategies are also optimistic in our case. To mitigate this optimism, we propose admissible winning strategies that are admissible and winning whenever possible. Further, we show that admissible winning strategies have the same computational complexity as admissible strategies and can be computed with minimal overhead. Let us now illustrate the emergent behavior of admissible and admissible winning strategies on two case studies. Note that a winning strategy does not exist for any of the scenarios we will discuss. Consider the same grid world scenarios before. The task for the robot is to reach the goal region while avoiding the environment player. Note that the environment player cannot block the goal region. The orange tiles are lava blocks that the robot should never enter. Each agent can move in one step in each direction or wait in the same cell. When the budget is 5, no winning strategy exists from the initial state. An admissible strategy, as shown on the left, is to go north and hope that the environment player cooperates. As you can see, the admissible strategy allows the system to reach the goal region. When the budget is 12, a winning strategy from the initial state exists, and the winning strategy is to go around. However, an admissible strategy assumes that the environment will cooperate and go north, as you can see. Thus, admissible strategies are overly optimistic and do not ensure task completion even when a winning strategy exists. For the same budget, an admissible winning strategy commits to going around the lava blocks irrespective of the environment player actions. Thus, admissible winning strategy are not overly optimistic and winning whenever possible. Let us now consider a slightly different grid world scenario. The goal is to show that admissible winning strategy are not only winning, but also seek cooperation whenever possible. The task, the actions, and the action costs are the same as before. Similar to scenario 1, we give a budget of 12 and illustrate the emergent behavior. For the admissible strategy on the left, the emergent behavior is as follows. The robot first goes north and then tries to evade the environment player. From this state, the system player can commit to a solid white strategy, which ensures winning, or choose the dashed white strategies, which is cooperative optimal, but mandates that the environment player cooperate. As illustrated before, admissible strategy chooses the cooperative optimal strategy and hence reaches the goal state. For the same budget, an admissible winning strategy commits to a winning strategy which goes through the opening in the middle. Let us now consider another rollout for the same strategy. The rollout is same as before. At this point, robot has multiple strategies to choose from. There are two strategies corresponding to winning strategy on the right. Here, strategy 1 is not admissible because if the environment player cooperates by staying in the bottom left, system performs worse than going north. Next, consider two strategies in the dashed white line. While these strategies are cooperative optimal, strategy 1 is not winning. Thus, it is not admissible winning. Thus, an admissible winning strategy commits to going north and observes what the environment player does. As the environment player chooses to stay in its cell, the system strategy to go east is not admissible as it does strictly worse than going west. Thus, an admissible winning strategy is not only winning and admissible, but also commits to a strategy that safely maximizes the chances of finishing the task with lower payoff if the environment player cooperates. Next, we consider a human-robot interaction scenario where there is a robotic manipulator and a human operating in a shared workspace. The task for the robot is to build an arch with either box's support and a box or a cylinder on top. It is preferred for the box to be placed on the top as it is more stable. We express this preference by modifying the action cost and making it more expensive to transfer and place the cylinder on top. The initial setup is shown on the left and a sample final configuration is shown on the right. Note that we allow the human to intervene and move objects back to its initial position. Thus, a winning strategy does not exist. A rollout of an admissible strategy can be seen on the right. We can observe that the robot reacts to the human interventions before placing the block on top. Finally, a subset of admissible strategies, specifically versus cooperative optimal, which will commit to placing a box on top as this ensures task completion with smaller total payoff if the human cooperates. Now we show a rollout under best effort strategy. As best effort does not account for action cost, the strategy is to place either a box or a cylinder on top. As we can see, the robot places the cylinder on top and eventually finishes the task. In summary, in this paper, we propose a novel framework for synthesizing admissible and admissible winning strategy for robotic tasks that must be accomplished in finite time with quantitative constraints. We give the necessary and sufficient conditions for the existence of both these strategies and give simple yet efficient synthesis algorithm. We show that admissible strategies can be overly optimistic and propose admissible winning strategy that mitigate this optimism. Thank you.